So we move this around. So see, the first term can be you do a conditioning. You do a you condition. Okay, you do a unconditioned. Okay, so this guy, if you add another layer of expectation, you remove the y, right? So exy is equal to e of xy given y. That's this, right? See, you start with the blue one and you add another layer of expectation, you remove the y and you have a clean expectation, no problem. Okay. Similarly, right, ex, you can rewrite it as e of ex given y. Conditioning and unconditioning, you go back and forth. Okay. For this blue line, for this blue term, y is given, so my y here in the first part can be moved out because it's treated as a constant, so the y can be moved out of the inner expectation, so y goes here. Is e of y times ex given y. Okay, so what do we have here, right? We have an expectation of a product of two random variables. One is y, the other one is ex given y. It's okay, right? This other thing is a function of y, so a y multiplied by gy. Here, e of gy, e of y. So what are we computing? We're computing the covariance between this guy and this guy. That's all, right? Covariance between this gy with what? No problem, right? Okay. Next, by the conditional variance formula, the e of a variance is equal to the variance minus the variance of e. Right? So compare with this formula, this is our statement, right? All we need to show is this formula. Why? Okay. So this statement involves the expectation of variance. You move this term to the right hand side, you get this term, right? So you move this term to the right hand side, combined with this variance, you have this term. Sorry, I mean, oh, no. This guy matched with this guy. This term matched with this term. I want to show inequality. All that I need to compare is this term with this term. Right? So all I need to show, in order to show the blue formula, I need to show the variance, this guy, is greater than this guy. Right? Very simple, okay? So why do we have this, right? Why do we have this? This is just trivial. This trivially holds, right? See, in order to show this, because we just argued that this numerator is equal to this more complicated covariance, right? So this covariance, according to this line, we can rewrite this as the more complicated covariance square. Okay. Or equivalently, dividing both sides by variance of ex given y, we have 1 greater than or equal to this numerator divided by this denominator and this term. Right? Dividing this term on both sides, we have this inequality, which holds trivially. Why? This is nothing but, the right hand side term is nothing but the correlation of these two random variables squared, which we know always holds, right? The correlation between two random variables is always bounded between -1 and 1. Question?
How to explain the covariance of x, y, the last two
Here?
equations? Yes. How to explain these two covariance is equal?
This one equal? Here, I will prove it. Covariance of x and y is equal to covariance of ex given y and y.
Okay.
So we replace this with this more ugly covariance term. So this is why we have this line, right? Then we divide both sides by this variance, then we have this one, right? But this term is nothing but, this is the square of the covariance, this is the square of one standard deviation, this is the square of another standard deviation. So the right hand side is the row square. And this holds all the time, right? So yeah, we got it. Okay. If this is always true, why do we even need control variate? Why don't we just do stratified sampling? Because theoretically speaking, the stratified sampling estimator always has a smaller variance than using y as a control variable, right? The issue is, the condition to treat y as a stratified sampling estimator is much stronger. You need to know the distribution of y, you need to know the pi. Here, treating y as a control variable, you only require the knowledge of the expectation of y, right? Also, you need to be able to simulate y. So the two methods, you have different assumptions. So you have to think about which one you can use when you're facing a realistic problem. Right? Some people, some y you can simulate, some y it's expectation, some y is probability mass, right? And sometimes you are able to simulate x when y is given. Sometimes you cannot do that. Okay? This is only a theoretical result. All right. What if we want to do a stratified sampling on a continuous random variable? Right? We only discussed the case where y is discrete. So meaning that y has a probability mass, the probability y is equal to small yi is equal to pi. What if y is continuous? We can still do this. So in the discrete case, we need to be able to estimate e of x given y equals k. Right? So when y equals k, you simulate ID copies of x and you average and you get this sample mean estimator for this guy. When y is continuous, all you need to do is to have a finite number of cases. Each case is classified by letting y fall into this small interval. So delta k can be an interval from A to B, for instance. Suppose we can generate y by inverse transform method, right? So let's say y is a continuous distribution, so we can do inverse transform using a uniform seed. Right? Generating yi, what is y? Y is a conditional version of y given that y falls into this interval. Generating such a yi via a uniform distribution, okay? So probability y belongs to this delta I is pi. You need to know that. You don't know this pi, you can't do stratified sampling. We can sort of let pi be 1 over k because you have freedom to choose this interval. So how large should the interval be? You can just make sure that the interval, the probability falls into this interval has the probability p, and p is evenly spaced. P is equal, right? So for instance, yi is the inverse transformed uniform, right? So what is this uniform? If ui is a uniform, then ui plus I minus 1 over k would be a uniform distribution between I over k and y minus 1 over k. I'm doing a shifting and stretching, that's all. That will give me a conditional distribution of y, given y falls into a delta I. Okay. See? This guy falls into the interval g minus of this value and g minus of this value because those are the extreme values of this term. Okay. So this will be the ith interval, right? Because yi falls into this interval, so this is the ith interval. So delta I is the interval g inverse of this interval. So the second step, right? So step 1 aims at explaining how to simulate a y given that y falls into the ith class, the ith case. So you still have cases just like the discrete case, except that right now the case is classified by this continuous interval. So delta I can be an A1 to B1, delta 2 can be A2 to B2. It's just the B1 is equal to A2, right? A1, B1, B1 is equal to A2 to B2, and continue. Right? Step 2 involves the generation of ith conditional on the event y falls into the ith interval, and you allocate NPI many copies if you wish to do PSS, the proportional stratified sampling, and you compute the sample average, sample mean, which is the unbiased estimator of this quantity, right? Given y falls into the interval delta I, and what is the expectation? You do this, right? Then the stratified sampling estimator would be the aggregate version, which is the same as before. The only difference here is that you have to discretize the continuous domain. I will have an example later to illustrate this. here's a quick example. We have a sequence of examples here. Customer arrive at an infinite server queue according to a Poisson process with rate lambda. And lambda here is a random variable. Lambda is equal to 12 or 4. And there's some probability, right? So on a good day, lambda is big. On a bad day, lambda is small. So let's say good day means good weather and bad day means bad weather. And on good weather, people go out and shop, right? If this is a shop, then you wish you have good weather. So each day is good with probability half and independent of the previous day. So it's bad with probability half. Okay. Service times on all days are exponentially distributed with rate 1. You can imagine that a customer enters a shop and spend an exponential amount of time shopping, then they will leave, right? That's why we model this as an infinite server queue, right? Okay. So every day at a time t equals 10, the system is shut down and all these presently in service, all those customers presently in service are forced to leave without completing their service. Let's say 10 at t equals 10 and stop service, removing all the customers. Estimate theta equals ex, and x is the number of customers in a day who do not complete their service. Basically, we are estimating the expected number of customers who arrived by 10 but still in the system in service before they complete service. They haven't completed their service, but they arrived. Okay. So this is a queue length function of an infinite server queue. This is something we studied before, except that this is a Poisson arrival with a random arrival rate. So, okay, so it's obvious to see that x is strongly correlated with lambda. If lambda is big, x is big. If lambda is small, x is small, right? So the brute force method or the crude multicolor estimator would require us to estimate lambda first. So flip a coin to decide lambda is 12 or 4. Then use the corresponding result, either 4 or 12, to conduct the simulation. That's the brute force one. We're not going to do that. I mean, we could do that, right? But we're going to stratify on a y random variable equals 1 or 0, right? So this is our stratified sampling estimate. This is our stratification variable, right? So we're going to condition on whether today is good or bad. Okay? Recall from 760, we know how to deal with the infinity queue. So we have a Poisson arrival, we have exponential service, we have infinite service capacity. Okay? With an arrival rate lambda, which is fixed, and service rate is equal to mean. We know that the qt, at the fixed t, the qt, the total number of customers in the infinity queue, is a Poisson random variable whose mean is equal to lambda times the integral of the g bar, and here g bar is the CCDF of the exponential. For exponential random variable, this g bar is equal to e minus mu x. Right? This is something we derived before in the stochastic model class. Okay? So you can compute this in this case, right? So if you just solve this integral, you have a Poisson random variable whose mean is lambda times 1 minus exponential function. Alright, so given x equals 0, x will be a Poisson random variable having this mean, because you know the mean depends on lambda, and lambda can be 4 or 12. Given y equals 1, I mean I don't need to create a y, right? I can just use lambda as my stratification variable, right? I can just say lambda equals 4 or 12, so x given lambda equals 4 is a Poisson random variable this, or x given lambda equals 12 is one random variable this. Doesn't matter, right? So y and lambda have the one-to-one correspondence, right? Doesn't matter. Because Poisson random variable has equal means and variances, so we know the mean, the conditional mean in the first case, in the y0 case, is just a conditional variance, right? Mean and variance are the same. Poisson has equal mean and variance. So okay, so in this case, the mean is 4 times 1 minus e minus 10, so the conditional variance is equal to 4 times 1 minus e minus 10. The other case is similar, right? So we have the conditional expectation and the conditional variance both computed. First, the variance of the stratified sampling estimator, we know that this is equal to this, right? This is equal to, this is, you know, we have the variance reduction, so we only have one term, right? So this is the variance of the stratified sampling estimator. That's this. This guy is equal to the variance in the first case times the probability of the first case plus the variance of the second case times the probability of the second case. Plug in the numbers, you will be able to see this is A times 1 minus E minus 10, which is about 8. Okay, combining the two terms. Next, let's compute the variance of the raw Monte Carlo estimator. Okay. To compute that, we need to add the additional term, right? Because we know the variance of x is equal to this piece plus this piece. Let's compute the other piece. Okay. So how do we compute the variance of expectation of x given y? Right? Let's compute its second moment and first moment. Okay? So second moment. So ex given y squared is equal to this guy times a half, right? Y, right? Ex given y is this guy or this guy. So its expectation would be this guy times the corresponding probability plus this guy times the corresponding probability, right? If you wish to compute the second moment, you have to square this guy, right? I'm computing what? I'm computing the expectation of this guy squared. So I'm gonna have to add up the square of this times the corresponding probability with square of this times the corresponding probability, right? So I'm gonna have this thing squared 1/2, this thing squared 1/2, which is equal to this. The expectation is easy, right? You don't have to square it, though. You just add up and divide by 2, right? 1/2, 1/2. So you can see that the variance of a conditional expectation is given by this thing. So the overall variance according to the conditional variance formula is equal to the summation of the two, that gives you 24. So the crude Monte Carlo estimator has about 3 times